Hello. So this is part 3 of the Minimapper project. Part 2 was just some written notes about the theory of DC motors and motor drivers and things like that. I don't really know what to call these episodes, parts, whatever, but this is number 3 anyway. So today I'm going to talk about choosing a motor driver. And this turned out not to be as hard as I thought it was going to be. I looked at a lot of data sheets, probably 25 data sheets or so. And so it was a little bit tedious, but I've chosen one, and we'll talk about it now. So first thing, what do you need for a motor driver? In our case, we've got 2 wheels we want to drive on a robot, so we need 2 channels. I don't know if it's better to have 2 single-channel drivers or 1 dual-channel driver. I tend towards the single-channel driver just because it means that you can make a circuit for driving 1 motor and then just duplicate it. We need something that has the right supply voltage. These motors run off of the recommended voltage is 4.5 volts, so we'll do that. We need something that can supply enough current, but that's not going to turn out to be a problem. In our case, we only need a maximum of 250 milliamps, and a lot of these things will drive 1.5 to 3 amps or more. We need a decent control interface. We want to be able to control the motors in detail, forwards, backwards, the different ways of braking and coasting, and we want to do it all with PWM. It'd be nice to have some kind of overcurrent protection and thermal protection and things on the drivers, just so we don't muck things up too much. One thing I want to be able to do is current sensing. So for a DC brushed motor, or any DC motor, the torque exerted by a motor is proportional to the current through the coil. So I quite like to do some experiments to try and characterize that relationship for the motors I'm using. So that means you need to be able to sense the current through the coil. And I learned something about this when reading these data sheets, and it looks like that should be easy to do. The other thing is having a sensible package for the motor driver, and that turned out not to be a problem either. So I learned a few things looking at all these data sheets. It was quite enlightening. One thing is that more or less all of these drivers incorporate a dead time mechanism. If you looked at the notes about motor drivers, or you know anything about H bridges, then you know that there's this dangerous state you can have where you switch on both the high side and low side FET on one side of the H bridge, and that gives a direct route from the positive rail to ground, which is bad. So if you're designing your own H-bridge from discrete FETs and your own control circuitry for that, you need to be careful that you don't ever get into a state where both FETs on one side are on at the same time. And so you need to sequence the switching on and off of the different signals to the H-bridge FETs quite carefully. Most of these drivers basically deal with that for you. They introduce a dead time between different phases of the FET switching to make sure that you don't get into this FET shoot-through situation. The other thing most of these drivers do is something to do with current regulation. So you don't want to exceed the maximum rated current for your motor. And what a lot of these drivers do is to allow you to attach a current sense resistor in the current path through the motor coil, and then set, usually using some external passives, a current limit. And then if the current through the motor coil during PWM switching reaches that limit, the driver will switch off the FETs in the H bridge to limit the current. And they do this in a variety of different ways we'll talk about. The other thing that became clear after doing this was that 4.5 volts, which is the voltage for driving the motors that I'm using, is really low. It's right at the bottom end of these things, and that actually restricted the choice of drivers a bit. So like I said, I looked at maybe 25 data sheets, and I made a spreadsheet, which we'll look at now. So this spreadsheet, I searched on Mazda, and I found drivers from a few manufacturers. TI and Toshiba make more than anyone else, I think. I looked at one from Diodes Inc., one from Maxim, one from ST, and one from Rome. But TI and Toshiba are mostly the ones of interest. There are some single-channel drivers, some dual-channel drivers. They vary quite a lot in supply voltage requirements. Most of them have an internal regulator to generate logic supply for the internal control circuitry from the motor supply. Some of them don't, and you need to supply a logic supply and a motor supply. The current drive from these things is plenty for our purposes. This thing about modes, so some of this stuff was filled in as I was learning how these things worked. So these modes of operation are about things like, does it support just standard PWM operation? Does it have some kind of current regulation set up and there are different approaches to handling the current regulation. And yeah, it's all reasonably straightforward, but it took a while to figure it out. Then there's the interface that you use to control this thing. There are two standard-ish ones. This one that's called In1 and In2. It seems to be the most popular. There's another one that has PH and EN. And then there's some weird ones. Virtually all of these things can do PWM. There are a few very low-end ones that just do on and off switching, but almost all of them do PWM. I was learning about current sense as I was reading these things, so this column ended up not being super relevant, but a lot of them can do current sensing, and you can set them up so that you can capture the current sense data yourself as well. Most of them have some kinds of protection, under voltage, over current, thermal protection. Some of them, the ones that are marked in bold and italics, have a pin that comes out when there's a fault. It has a signal on it that when there's a fault that you can use as an interrupt on your microcontroller. And then packages, they vary quite a lot. So after looking at all of these things, I just started looking for reasons to reject them. And some of them I could reject immediately because the supply voltage requirements just didn't fit the motors. Some of them are rejected based on the fact that they only did the most basic of PWM, or I couldn't quite figure out what they did. Some of them I rejected on the basis of packages. I'm almost certainly going to end up using some small packages for some of the mini-mapper stuff, but for these early prototyping things, I want to make life easy for myself. So I'm avoiding these smaller things for now. There are a couple of price outliers that I rejected. One of them was a Maxim part, unsurprisingly. And then this Diodes Inc. part had a weird interface compared to the others. So I was left with 4 on my short list. 3 from TI, 3 dual drivers from TI, and 1 single channel driver from Toshiba. And I picked the Toshiba part. It's a single channel driver, which is fairly suitable for what I want to do. The supply voltage is fine, the current drive is fine. It has one of these current regulation modes, which I'm going to use. It has a standard interface, does PWM, it has protection, and it's in a super package. So I like that. So let's take a look at the data sheet for this thing. So one thing I noticed when looking through these things is that the TI data sheets are really good, and I've seen that before. They're very nice, and the Toshiba ones I was a little bit on. And then I discovered that the Toshiba English data sheets are actually translated from the original Japanese ones, which is why they're sometimes a bit funny. But my Japanese isn't good enough to read the other ones, so I have to stick with this. And it's not bad. And there's some other documentation provided by Toshiba. There's an application note that goes with this part. And there's quite an interesting catalog of their motor solutions that is worth a look at. And I'll put links to those on my website. But look at this package. It's a nice 8-pin SOIC. You can't really complain about that. Easy to solder, no problem at all. So we'll be going over more of this stuff when we come to the schematic capture. But let's just take a quick look at the block diagram. So you've got 2 inputs. And there's a table in a minute that shows what these mean and what they do. You've got 2 outputs that drive the motor. You've got an H bridge that the motor's connected to. You've got a single supply, and you've got an internal regulator that regulates that supply down to run the control logic. So it's simple. The H bridge, in the notes that I made, I showed an H bridge that had N MOSFETs on the low side and P MOSFETs on the high side, which makes driving the gates of the things easy. If, as in this case, you use N MOSFETs for the high side, you need some kind of gate driver to be able to drive the gates above the source, and that's what this charge pump here is for. There's some protection stuff, under voltage, over current, thermal, and then you have a sense resistor that's in the current path coming out of the motor, and that allows the logic in here to sense the current through the motor coil, and you set a reference voltage to compare that with, and there's a formula that tells you what the combination of reference voltage and sense resistor means in terms of the maximum current that's allowed. So that's really handy. And what happens when, let me just show you, I'll scoot down to this thing. So when this overcurrent thing happens, I don't know why it's labeled NFTH, there's probably a reason for that, but it's basically the maximum current that's allowed through the motor coil. If the driver detects that the current through the motor coil has reached that limit, it switches the FETs in the H-bridge off for a fixed time. Half of that time is in the fast decay mode, so where all the FETs are switched off and the motor coil current flows through the freewheeling diodes in the H-bridge in the opposite direction to the supply, and that's the fastest way of braking the motor. Braking in the sense of slowing down, not busting it. And then the second half of this off period is in the slow decay mode, where both of the low side FETs are on, and you get current recirculation just through the motor coil and the on resistance of the low side FETs. And there's a whole bunch more in the data sheet about how this mechanism works, but it's a good way of making sure that the current through the motor doesn't get high enough to cause any damage. The other thing to look at is this description of how the interface works. So you have two pins, in one, in two, and these things that are marked out one, out two are really the states of the FETs driving the motor. So for forward, you have one high and one low, and that drives current, say, in the direction through the motor coil that causes clockwise rotation. Switch them around, current is driven in the opposite direction. When you want to do PWM, you hold one high and you do your PWM on the other one. And having these two inputs means that you also have access to a braking mode and basically a coast mode. And so this is just about the simplest control interface for these things that there is. So we'll go more into this when we get to looking at schematic capture for the motor driver board. And so it wasn't too hard to choose this part. It was boring because I had to read lots of motor driver data sheets, and there really are quite a lot of them out there. But I'm now at a point where I feel comfortable about starting schematic capture for the motor driver. And so in the next part, which will be in a couple of days, I'm going to go over some KiCad setup for library management and things like that, because I'm going to be making quite a few boards on this project, and it would be good to have a coherent way of managing the components I'm using and have some templates and things. So that's what we're going to do next time. See you then.